Hey everybody, so we're going to go over how to do some strong acid-base problems. Instead of having my floating head, I have my handy-dandy little calculator here. I can show you how to do some of the math problems. So we're going to do question 16.43 in this video. I'm going to go over the math of how to do it. It says calculate the pH of each of the following strong acid solutions. So, in order to do that, we have to keep in mind there's a principle here that the concentration of the hydronium ion is always equal to the concentration of the strong acid. For weak acids, that's a little bit different. So be careful, but for strong, as long as it indicates a strong acid, or you've memorized the 7 strong acids, then you know that the concentration of the strong acid is equal to the concentration of the hydronium ion, and that makes it a little bit easier to deal with. So what are some of the examples? It says 8.5 times 10 to the minus 3 molar HBr. Okay, so 8. So part A, this is for question number 43. So this is double check that I have the right answer. 8.5, sorry, not the right answer, the right question. 8.5 times 10 to the minus 3 molar HBr. Okay, so now what do we do here? Woo! Move that. Okay. I want to make sure that I have a lot of room here. Woo! Put my calculator back in the screen. Okay. So, well, remember that pH equals the negative log of the concentration of the hydronium ion. Well, if we have the concentration of the acid, then we can definitely figure out what the concentration of the hydronium ion, because they're the same. So in this case, the pH equals the negative log of 8.5 times 10 to the minus 3. And so now when we plug that in our calculator, we get negative log of 8.5. And now I always use E, okay? That makes that all one term, and it doesn't split it up and do the math funny in terms of orders of operations. So there's E, and then negative 3, end parenthesis, and we get a pH equal to 2.07. Okay, so we just use significant figures. Okay, so part B, that says, oh, now we're in grams. Okay, 1.52 grams in 575 milliliters. So down, so it's, of course I forgot here, 1.52 grams. So 1.52 grams in 575 milliliters. Okay. Now the acid in this case is, so this is part B, is HNO3. That's nitric acid. So is nitric acid a strong acid? Yes. Okay. So you get out a periodic table, and we have to figure out how to get concentration. Okay. The concentration, the molarity equals, and for some reason I only do this for this one, but I always use the units, and so it's always moles per liter. Well, we have liters, or we don't, we have to convert. Okay, so we can convert this to liters, so by moving our decimal point over 3 spots. So we now have liters, so the volume equals 0.575 liters, and now we need the number of moles. Well, we can't get the moles until we convert this to moles, and we do that by using our molar mass. So now this problem becomes kind of even more of a big pain in the neck because we have to calculate a molar mass and then convert to moles. So let's do that. So H is equal to 1, and I'm just going to round to whole numbers. That the mass of that, we look at our periodic table, then we get that that's equal to 1. And there are 1 of them, so that's 1. And for nitrogen, the molar mass in the periodic table is 14 times 1 equals 14. And then oxygen is 16 times 3, and that equals 48. So we add up 1, 14, and 48. 1 plus 14 plus 48, and we get 63 grams per mole. Now we have to convert 1.52, and I like to use the X line. Okay, so 1.52 grams, X line, grams over moles. Looking at this, where's the grams per mole? Where's the grams? 63 is equal to 1 mole. And so now we do that math, 1.52 divided by 63. And so what we have is we have 0.024, one more sig fig, 1 moles. Okay, we're still not done because now we have to calculate the molarity. So it's 0.02. Let me write this a little bit better here. Okay. So this one is 0.0241 moles, which we got from here, divided by, let me see what, okay, this number in liters, 0.575 liters, and so 0.0241 divided by 0.575, and when we get that, we get that equal to 0.0419 molar. Now we're still not done. This is a strong base, or strong acid, sorry. And so strong acids mean that the concentration of the acid is equal to the concentration of the hydronium ion. So pH equals negative log of concentration of the hydronium ion. And so that means that it's negative log of 0.0419. And so that's negative log, and I'm going to do a trick here. I'm going to use the answer, so the one above it, okay, and that pH is equal to 1.378, okay, and that is your final answer. Okay, so part C, okay, that says 5 milliliters of 0.25 molar is diluted to 50 milliliters. Okay, so now this is going to be kind of an interesting problem. That's okay. So this is part C. Okay, and so is it a strong acid? Of course, because we're in the strong acid, but it's 5 of 0.25, so this is 5 milliliters of 0.250 molar HClO4 is diluted to 50 milliliters. And so now this is a dilution problem, because again, the chemical concept that we're trying to hammer home with this problem is that as long as you have the concentration of the strong acid, you can find out what the pH is. But now we're diluting the acid, so because we dilute it, we've changed its concentration. So we dig back into our notes, and we find that anytime we do a dilution, the formula is M1V1 equals M2V2, where this one would be the molarity and volume of it beginning, and this is the molarity and volume at the end. Okay, So I'm going to clear out the calculator because we're going to need to use this. Okay, so let's do this. So what is the initial molarity? 0.250. What is the initial volume? Okay, 0.005 liters equals, we're trying to find what the new molarity is, M2, and we converted this to liters. And now we convert this to 0.050. Okay, so now we do math. We math it. Okay, as soon as we get to this point, now we know that M2, the new molarity after it is diluted, will be 0.250 times 0.005 divided by 0.050. And so our new molarity is 0.025 molar. Now, let's just quickly take a minute and understand the logic of that dilution. Look, 5 milliliters going to 50, that's a dilution factor of 10. We're diluting it 10 times. And what's the difference, or what is the factor that the molarity is changed? By 10. So that makes sense. So now we're going to calculate the pH. pH equals the negative log of the concentration of the hydronium ion. And so that equals the negative log of 0.025. And so now, let's see, negative log of 0.025. Now we get 1.60. Okay? So now let's take a look at part D of this question. Okay? The solution is formed by mixing 10 milliliters of HBr with 20 milliliters of 0.2 molar HCl. Okay, so this is kind of interesting. Okay, so for this question, let me get a new sheet here. Okay, so for part D here, we have two acids. We have 0.1 molar, and we have, what was it, 100 milliliters or 10 milliliters? Let's see, 10 milliliters of HBr. So this is 10 milliliters of HBr. And then we have 20 milliliters of 0.2 molar HCl. Okay? Now we want to find out what the pH is. Well, this is actually one of my favorite types of problems. Okay? 10 milliliters. So, what we're doing is we're adding two acids to find out what the new concentration of hydronium ion is. Okay, so this one's going to be a little bit different. Okay, in order to do this, we need to know how many moles of H3O plus there is for liters of the solution. Now, we have how many liters of solution there are. Okay, that's kind of straightforward to figure out because we have 10 milliliters of HBr plus 20 milliliters of HCl, so that's going to be 30 milliliters, which equals 0.030 liters. Okay, so I'm okay with that. Okay, but how do we figure out how many moles of H3O plus there are? Well, can't we figure out how many moles of H there are because of the HBr? And can't we figure out how many moles of H there is because of the HCl? And add those together? Of course we can. So let's take a minute and let's do that. Okay, because that's what we have to do for this problem. So for HCl, let's do HBr first. Okay, so we have 0.010 liters. We're going to X-line it, and for every 0.100 moles, that's in 1 liter. So it's 0.01 times the molarity, 0.1. And so the number of moles here is 0.001 moles of H3O plus. That's just the number of moles that HBr is adding. Now, how many moles is HCl adding? Well, this is 0.020 liters times 0.200 moles over 1 liter. This is the concentration. Molarity is moles per liter. Equals, okay, so 0.02 times 0.2. And this is 0.004 moles of H3O plus. So if that's how many moles of H3O plus we have, okay, now we can add those two together. The total amount of H3O plus is going to be this number of moles of H3O plus and this number of moles of H3O plus. So we have 0.005 moles of H3O plus divided by 0.030 liters of H3O plus. So it's 0.005 divided by 0.03. And so the concentration of H3O plus alone is going to be 0.166 repeating. Okay? That equals the concentration of H3O plus. Now that stands to reason, again, if we're going to do some logic, isn't this going to, the concentration fall between these two values? And this is 1/3 of the value, and this is 2/3 of the solution. 1/3 of the solution, 2/3 of the solution. So it's almost like we're taking a weighted average. Okay, so it makes sense that the concentration is this. So now, if we have this concentration, pH equals negative log of the concentration of the hydronium ion, okay, equals negative log of 0.166 repeating, okay, and so negative log, and in this case I'm just going to use second answer, and so the pH in this case equals 0.778. Okay, and so there's our pH, and double check life is good. Okay, so that's sample problem 16.43.